How does absorptivity affect radiation heat transfer? Imagine standing near a campfire and feeling the heat on your face. That heat comes from radiant energy traveling through the air. Now, think about how different surfaces soak up or reflected that energy. That's where absorptivity plays a key role. Absorptivity is a property of a material that tells us how well it absorbs incident radiation energy. It's expressed as a fraction, meaning if a surface has an absorptivity of 0.8, it absorbs 80% of the radiation hitting it. The rest is reflected or transmitted. This property is essential when designing systems that involve heat transfer through radiation. In radiation heat transfer, energy can be emitted by a surface, transmitted through space, reflected away, or absorbed. Surfaces with high absorptivity soak up most of the incoming radiation, which raises their temperature. This means they gain more heat from radiation. On the other hand, surfaces with low absorptivity reflected or transmit more radiation, so they don't heat up as much. The relationship between absorptivity, reflectivity, and transmissivity is simple but important. The sum of these three properties equals 1. For opaque materials, transmissivity is 0 because no radiation passes through. So, the sum of absorptivity and reflectivity is always 1 for these materials. This helps engineers predict how surfaces will behave when exposed to thermal radiation. In practical terms, if you want to maximize heat absorption, such as in solar collectors, you choose materials with high absorptivity. These surfaces are often painted black or coated with dark finishes because dark colors absorb more radiation. Conversely, to reduce heat gain, surfaces are coated with reflective or low absorptivity finishes, like shiny metals or white paints. Absorptivity also varies with the wavelength of radiation. Solar radiation has a different spectrum than thermal radiation emitted by objects on Earth. So, materials are often tested for their spectral absorptivity to match specific applications. For example, solar panels are designed to absorb visible and near-infrared wavelengths efficiently. Understanding absorptivity helps engineers control temperature and improve energy efficiency. For example, in designing insulation, surfaces with low absorptivity help keep heat out. In heating systems, high absorptivity surfaces help maximize heat transfer from radiation. Emissivity, which is closely related to absorptivity, also matters. According to Kirchhoff's law, at thermal equilibrium, a surface's emissivity equals its absorptivity at each wavelength. This means a surface that absorbs well also emits radiation efficiently. In summary, absorptivity determines how much radiant energy a surface absorbs. This influences how hot the surface gets and how much heat is exchanged through radiation. It's a vital property in designing thermal systems, from solar collectors to insulation, helping us manage heat flow effectively.